Here we're given an equation, x squared plus y squared equals 9, and we're asked to determine this funky notation here, d squared y over dx squared. This is really just math talk for a second derivative. Oftentimes when you were first learning second derivatives, you would probably call it something like f prime of x. But if we're using our differential notation, dy dx, then a second derivative in that scenario looks like d2y over dx2. So here we're being asked to find a second derivative. When we look at this equation, what we're going to notice here, x squared plus y squared equals 9, is that we have x's and y's sort of what I call commingling. We've got them all mixed around in this problem, and there's no way to separate this thing out, right? Up to this point in this class, you've seen a lot of equations that are y equals, some crazy stuff over here, and the y was on one side, the x's were on the other, and we found the derivative of that using our standard methods. Here we have x's and y's working together in a problem, and we can't separate it out to get a nice clean y equals, but we still need to find the derivative like we've been doing. That's when we run into this process called implicit differentiation. We're going to wrap this thing in a set of parentheses, and we are going to dx it. We know to dx it because of what's going on the bottom here. They're asking us to find the dx squared piece. And so that is telling us that what we want to do is dx this entire equation. Whatever's on the bottom there is how you want to address the equation. When I do implicit differentiation, I've got a little saying that I use, and my saying just goes, every time I take a derivative, I get extra stuff. So every time you take a derivative running this process, you're going to get extra stuff. And what that extra stuff is going to look like is just sort of envision there being this little box on the top here. And we're always going to fill that box in with whatever the letter is we took the derivative of. So what that looks like in practice now is we are going to ddx this thing. So we take the derivative as you normally would. The derivative of x squared following your power rule would be 2x. We took the derivative of an x, so we get dx over dx. We filled that box in with an x. Then we're going to get plus, take the derivative of y squared, we get 2y. Again, took a derivative, get extra stuff. Took the derivative of a y, so I get a dy dx. Fill in that box in. Equals, and then the derivative of a constant, the derivative of a number, no matter what method you're using, is always 0. After I do this, I like to do what I call a cleanup step. So oftentimes when you're doing implicit differentiation, you just really want to put the right pieces in as you go, and then come back and clean it up and make it more user-friendly for you to do some algebra. So working my way through this left to right, I've got 2x, and then dx over dx can cancel out. That's like having 5 divided by 5. It ends up being just 1 when you cancel those things out. So dx over dx cancels. We get plus 2y dy dx, and all of that equals 0. So not a lot to simplify, but it's always worth going through a simplification step on this. From here, in order to find a second derivative, we have to get our first derivative. We need to find out what dy dx is. And so the process on this is going to be to solve to get dy dx by itself. So this is just an algebra problem from here. So we want to treat dy dx like any other variable and just get it alone on one side of the equals. We're going to move everything else away. So I'm going to minus my 2x over to the other side. We get 2y dy dx equals negative 2x, and then you're going to go ahead and get rid of that 2y, so divide by 2y, and we end up with dy dx equals, we can cancel out those 2's, this is going to be negative x over y. So that is our first derivative, right? That is dy dx, that's like having f prime of x right now. And so what we have to do to finish this thing up, they didn't want the first derivative, they wanted us to go through and find the second derivative. So to find the second derivative, you're just going to take your first derivative, and you're going to take the derivative again. So again, you're just going to wrap this thing in a set of parentheses, and you're going to ddx it. So coming through, you can kind of see where this notation comes from now. We have d, and d is going to get us d squared y over, and then dx is going to get us dx squared. That's where that second derivative notation comes from. Equals, and we come over here now and we look at this and we say, remember, product rule, quotient rule, chain rule, all these rules still apply when you're doing implicit differentiation. So when I look over there and say, well, how do I take the derivative of negative x divided by y? That's telling me that I need to go apply my quotient rule. I have two things being divided. And so the quotient rule saying that I use goes low d high minus high d low, and all of that is over the low squared. I label the top piece the high piece. I label the bottom piece the low piece. And then I run through this rule. And it's only when I go to find the d high, the derivative of the top piece, the high piece, that's what I mean by d high, that's when I'm taking a derivative and I get my extra stuff. When I take my d low, when I find the derivative of the low piece, that's when I'm taking a derivative, and that's when I get my extra stuff. So now we just follow our quotient rule to get to where we need to be. It says low, all right, so the low is y. Then it wants d high. The derivative of negative x would be negative 1. I took the derivative of an x, so I get a dx. Every time we take a derivative, we get extra stuff. So then we're going to get minus from our rule, then go grab the high piece, which is negative x, and now multiply it by the derivative of the low, the d low. So the derivative of y would be 1. Took the derivative of a y, so you get dy dx. And then all of that is over the low squared. So all over y squared. From here, the next move that you want to do whenever you're doing implicit differentiation, after you run through the process and put the pieces in, just put them in as you go. Don't worry about simplifying in the middle of it. Now is when you'll do your simplification step. So now we're going to come through and just kind of clean this thing up. So we work our way left to right. We get our d2y over dx2 equals negative 1 times y is going to get us negative y. dx over dx, like we saw earlier, those just cancel each other out. We get negative x right here, and then that negative is going to turn it into a positive x, and then we have dy dx on that piece, and all of that is over y squared. Sometimes they're fine with you being done here. Oftentimes they want you to take one more step because we have a dy dx in our equation, and we want our equation to just be talking x's and y's. Well, guess what? We know what dy dx is. We found that out. We had to do that for step 1 of the process, finding the first derivative. So now you're just going to replace dy dx with what you know dy dx is. So we get d2y over dx2 equals negative y plus x, and then dy dx is negative x over y. We found that out earlier, and all of this is over y squared. And from there, it's really just how much simplification does your teacher want out of you. This is a good answer. If you needed to, maybe you'd multiply this. This is like x over 1 right there. So you can maybe simplify this down to being negative x squared over y, and all of that over y squared. You know, really it's personal preference. At this point, you've found the second derivative in terms of x and y, so really you're done. Thanks for watching my video. If you liked it, please click that like button and subscribe. And also share it with your friends and anyone else you know who might be crying about an upcoming AP Calc test. You can find more videos from me, more sample AP Calc questions, and my complete AP Calc study guide over at my website, apcalcprep.com. Have a great one.